explain Fleming's right-hand rule. So we have a short animation here where we have magnetic field and a conductor placed in the magnetic field, the copper colored rod, and we are moving the rod upwards with a force, and out comes a current from its edge. So let's start at the beginning. We have a magnet, a north pole at the far end, and we have a south pole at the near end, nearer to us. And you can see a blue arrow traveling from the north pole to the south pole. The blue arrow indicates the direction of the magnetic field lines. And the Fleming's right-hand rule is shown in the image where you can see a right hand and the forefinger is pointing in the direction of the magnetic field. And the conductor that's moved upwards in the magnetic field is indicated by the thumb. So there's a force acting on the conductor. So with these two inputs, the forefinger and the thumb, the output is the middle finger, which is pointing in the direction of the induced current. So Fleming's right-hand rule is all about the three directions which form the X, Y, and Z axis. Let's look at the animation again. Initially, the copper-colored conductor is stationary. Where it's stationary, although it's placed in a magnetic field, nothing happens. There is no force, so there is no induced current. Now we will apply a force and move the conductor vertically upwards inside that magnetic field. As soon as we start moving the conductor, you can see the green arrow coming out of the edge of that conductor. That shows that there has been an induced current created inside the conductor. You stop the motion and the current stops too. So this is the principle of Fleming's right-hand rule. Once again, to recap, we have a conductor at the bottom level between those two magnets, and there is no induced current. And as soon as we create a force in the vertical axis on the conductor to cut those magnetic lines, you get the induced current of the conductor. So no force, no current. And for a generator, we have to keep rotating the rotor and keep the conductors cutting the magnetic lines in order to get a continuous current. I hope this explains the Fleming's right-hand rule. Thanks and have a great day.
Fleming's right-hand rule. When will the induced current in the electric conductor or the coil be maximum? It will be maximum when the direction of motion of the electric conductor is perpendicular to the magnetic field. In order to show the direction of the induced current, Fleming's right-hand rule is very useful. Stretch the thumb, the index finger, and the middle finger in such a way that they will be perpendicular to each other. In this position, the thumb indicates the direction of motion of the conductor, the index finger the direction of the magnetic field, and the middle finger shows the direction of the induced current. This rule is known as Fleming's right-hand rule. Electric generator. We have seen the experiment based on electromagnetic induction. The current produced in this experiment was very small magnitude, but the same principle can be harnessed for the use of mankind to produce large current. Here, mechanical energy is used to rotate the current carrying coil in a magnetic field around the axle, thereby producing electricity. In the figure shows a copper wire coil ABCD kept between the two poles pieces of a magnet. The two ends of the coil are connected to the conducting rings R1 and R2 via carbon brushes. Both the rings are fixed to the axle, but there is a resistive coating in between the ring and the axle. The axle is rotated with the help of machine from outside. Because of this, the coil ABCD start rotating. The stationary carbon brushes B1 and B2 are connected to a galvanometer, which shows the direction of a current in a circuit. Upon rotating the axle, the branch AB goes up and the branch CD goes down. According to the Fleming's right-hand rule, electric current is produced in the branches AB and CD in the direction that is A to B and C to D. Thus, the current flows in the direction A to B, C to D. In the external circuit, the current flows from B2 to B1 through the galvanometer. If instead of one loop coil, a coil consisting of several turns is used, the current of magnitude several times flows. After half rotation, the branch AB takes the place of branch CD and the branch CD takes the position of branch AB. Therefore, the induced current goes as a D to C, C to B and B to A. But the branch BA is always in contact with the brush B1 and the branch DC is in the contact with B2. Hence, in the external circuit, current flows from B1 to B2, that is opposite to the previous half rotation. This repeats after every half rotation and alternating current is produced. This is what is called an AC generator. Children, now we'll see a video how electric generator works. So we'll understand better through this video.
Do you know how an electric generator works? Electric generator converts mechanical energy to electrical energy. An electric generator, as shown, consists of a rotating rectangular coil ABCD placed between the two poles of the permanent magnets. The two ends of this coil are connected to the two rings R1 and R2. The inner side of these rings are insulated. The two conducting stationary brushes B1 and B2 are kept pressed separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of the two brushes are connected to a bulb to show the flow of current in the given external circuit. When the axle attached to the two rings is rotated such that the arm AB moves up in the magnetic field, the induced current direction can be found by applying Fleming's right-hand rule. The induced currents are set up in these arms along the directions AB and CD. Thus, an induced current flows in the direction A, B, C, D. If there are larger numbers of turns in the coil, the current generated in each turn adds up to give a large current through the coil. This means that the current in the external circuit flows from B2 to B1. After half a rotation, arm CD starts moving up and AB moving down. As a result, the directions of the induced currents in both the arms change, giving rise to the net induced current in the direction D, C, B, A. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the polarity of the current in the respective arms changes. Such a current, which changes direction after equal intervals of time, is called an alternating current, abbreviated as AC. This device is called an AC generator. Download Spark.